Hello everybody, my name is Arielle Moreno and I'm a tutor for the Aspire program, and today we're going to be going over resonance structures. So from what I understand, a lot of students have a lot of trouble with this subject, so for this tutorial I'll just cover a couple of rules that you need to follow, and I'll also cover a lot of the big errors and mistakes students make while working with these structures, and also provide a couple of examples, alright? So for the rules, there's really only a couple of rules you need to worry about. It's really just two. So for the first rule is to don't break sigma bonds. Don't break sigma bonds. So for those of you that can't remember what sigma bonds are, it's really just a fancy word for saying single bonds. Single bonds. Alright? Now the second rule that you need to follow is the octet rule. Octet rule. So for those of you that can't remember Chem 1 or Chem 2, octet rule basically is says that every atom wants to have a full outer shell. So like in this case for oxygen generally has only 6 electrons. So because oxygen wants to have a full valence shell, it's going to grab two electrons from another atom in order to have 8 electrons. So remember that 8 electrons is what every atom wants, or at least for this course anyway. So now that we've gotten the rules covered, we're going to go over the mistakes. So the first mistake most students make are with formal charges. Formal charges. So for formal charges, a lot of students really don't understand the concept, or they forget that formal charges do change the structure and the bonds that are made. So for this example, we'll just go with carbon. So with carbon has only 4 valence electrons, which means it's only going to have 4 bonds. Now this is when it's neutral, when it's 0. Alright, but if a carbon has a positive formal charge, it's going to change. So instead of having 4 valence electrons, it's going to have 3. So it's 1, 2, 3. And because this one is empty, it's only going to make 3 bonds with another atom. The same can be said for a negative formal charge. So for negative, instead of being empty right here, it's going to have an extra electron. So it's going to have 5 valence electrons. However, this doesn't really affect how many bonds it's going to have. It's still going to have 3 bonds, just like the positive. The only difference being it's going to have a lone pair up here instead of just being empty. So just keep that in mind for all the atoms that you use. This includes oxygen, nitrogen, hydrogen, whatever it is that you're working with. So another huge mistake most students have are hydrogens. And what I mean by this is that a lot of students forget that hydrogen exists. So when you look at the bond line structure, like say for this example, each one of these lines represents a bond between a carbon and carbon atom. However, what you don't see is the hydrogens. So for right here on the sides, you're always going to have 3 H's, unless it's stated otherwise, like if you have an oxygen right here or a nitrogen, then that's a different story. But if it's blank, then you need to assume that hydrogens are always going to be there. And that's really the general rule for every bond line structure. And another problem, the last problem that most students make, is that they break the four bonds. So for most of the atoms here, they're only going to make 4 bonds because that's what they need to fulfill their octet rule, which was 8 electrons. So for another example, we can go right here and put a nitrogen. Sorry, that looked really bad. So if you have a nitrogen right here and it has a negative formal charge, it's going to have an extra lone pair. So for this resonance structure, you just move this electron pair and then you'll make a pi bond. However, most students, they sometimes leave it like this, and when they do, they don't realize that there is a hydrogen up here. So instead of having like a carbon with 4 bonds, you're going to have a carbon with 5 bonds. And this is a really big no-no, because that means it has 5 valence electrons and an extra 5. So to have 5 electrons in total 10, and that's not what the atoms want. All right. So keeping that in mind, I'm gonna start going over 2 examples. Okay, so the first example is pretty easy. It's your normal pentane, and we're gonna put a pi bond and a formal charge just to make things interesting. So when you start off with resonance structures, you have to make sure you put it in brackets, and make sure that you always have arrows pointing both ways. Because with resonance structures, you're not staying, or the atoms don't stay the way they are all the time. The molecules are always shifting. So in order to find this formal charge, in order to find the other state that it's in, you got to look at the formal charge. So this is the formal charge, right? And depending on the formal charge that you get, you're going to change how you're going to go about it. So since this one is a positive, that means the carbon here only has 3 valence. And if it's positive, you always go from any other adjacent bonds. It's going to go towards it. So you see right here is a pi bond, which means that there's like another pair of electrons being shared between this carbon and this carbon. So what you can do, since it's not technically a sigma bond, you can break that bond and move it over here. So when you do that, you're gonna have that pi bond go to the other side. But what you need to remember is that you need to keep your formal charge. So because you move these pair of electrons to the other side, this carbon now has 4 valence electrons. However, this one over here, it's going to end up with 3. So your positive charge is going to be on this carbon. All right? And that's really the basics that you really do need to remember. So we're going to start going with a little bit more difficult one, and this one's going to be an aromatic. Let's see, aromatic. And this one's going to have 2 pi bonds and a negative charge. So when you first start off with this one, since this one is a negative charge, you're going to start off over here. So this means that this carbon atom has an extra electron. So it has a lone pair right here. So what you do is, like when you have positives, you have to go towards it. So when you have negative, you have to go away from it. So what you can do is look at the adjacent bonds. So it'll be right here. Like these two are going to be the adjacent bonds. So this one has a pi bond and this one has a single bond. Well, the rule is that we don't break single bonds. So what you can do is move this pair of electrons to this side, and you can break this one right here. But when you break it, you can move it to the corner. So what ends up happening is it's sort of going to be like, it's going to look the same as this. It's just going to be a little bit more turned around. So for here, the pi bond's going to form over here, and this one's going to break. But you're keeping your formal charge. See, so when you have the resonance structure, it's always going to keep its formal charge. If you start off with a positive, it's going to be a positive. If it starts off with a negative, it's going to be a negative. So when you're at this stage, you have to figure out, well, can you make another resonance structure? And in this case, you can. So for here, since this is a negative charge, this is where you start. So you can move these pair of electrons over here. But since this one already has 4 bonds, remember you have the hydrogen right here. You have to break this bond and move it to the little corner over here. So you can make another resonance structure. Let's see, right there. So now that you've moved it, you still have this one, and you move the pi bond to this side. So you gotta remember, since you moved the electrons and you broke this bond, this one's gonna have the extra pair of electrons, which means it's gonna have a negative formal charge. And then once you get at this state, you need to think about, well, can I make another one? But since this one doesn't have any pi bonds on this side, but it has pi bonds on this side, you basically be going backwards. So before you stop and end it there, you need to put arrows going the other way. Because like I said, in the resonance structures, they're always flipping from one to the other structure. And that's the same for this one. These two are always flipping around, so that's really what happens. So if you have any other problems or if you have any other questions, you can stop by the Aspire Labs. It's C108, and that's at the Cortez Hall. All right, thank you, and see you in the next one.